All right, let's talk about the chi-squared analysis first. So chi-squared analysis, that is strictly to analyze the null hypothesis. And whenever we're writing a null hypothesis, it's basically always there is no statistically significant difference in the data. So point flip is the easiest to compare it to. So 50-50 is what we expect. 49-51, is that close enough? 48-52, I mean, what's the point to where it's not close enough? Obviously, if we have 25-75, is that close enough to 50-50? No, and that's obvious. But sometimes it's not obvious, and so that statistical analysis allows us to analyze that and come up with a conclusion without having bias. So I talked about at the beginning of the year that we all have bias. I mean, there's nothing you can do about it. We have bias. You've got bias. It's how you're brought up, raised, what you're around, the experiences that you have. There's nothing you can do about that. We just want to make sure that we don't apply bias in scientific analysis, because then that's like putting a little bit of an opinion on it. And so sometimes it's easy to see, but it's not always easy to see. Somebody might say, oh, well, 45-55, that's not close enough to 50-50. Whereas somebody else will say, yeah, that's close enough to 50-50. But that might be their bias, their opinion. If we run statistical analysis, we can take the opinion, the qualitative stuff out of it and say, okay, well, this says that it's not. And so nobody can argue with statistical analysis. Another good thing about the chi-squared analysis is it allows us to pick out data when there's variables that are affecting it that we don't notice. So the second pom-pom, or the first pom-pom draw, we had 4 little pom-poms, all the same size, different colors. So we're just looking to see how many of each. I think most everybody had the data failed to reject the hypothesis that even though the numbers weren't different, because in the pom-pom draw, we were expecting it to be 10 for each, right? But it didn't get exactly 10 for each, 9, 11, 7, 12, whatever. And that data, we ran it through, and I think everybody got on there that failed to reject the data. Sound right? For the first pom-pom draw. Makes sense. So even though the numbers are different, that's just up to chance. That's what that's saying. Second pom-pom draw. Now we introduce big boy, right? Generally speaking, just looking at this, which one do you expect to pick the most? Just looking at it, you expect to pick this one the most. It stands out the most. It's going to be the easiest to hit when you're drawing it from the bag. Makes sense, but that's applying bias to it. Did anybody have the second one where data failed to reject it? So Parker had it to where data failed to reject it. Now, the big one was a little bit heavy on picks for sure, but it wasn't enough to say that there was something else going on there. And I'll talk about that in just a minute. So let's take a look at the data was rejected, the data rejected the hypothesis. Data rejected the null hypothesis. Sorry, it's a good thing it's Friday. So what that's saying is that there wasn't some other variable influencing your draws. What was the other variable influencing our draws? The size was influencing our draws. That was easy to see. But imagine being out in the field somewhere. You're trying to control as many variables as possible. It's entirely possible that there's a variable that's affecting it that you have no idea that's affecting it. For example, once when we had the first pom-pom draw and the small ones, somebody had it run up to be the data rejected it because they never picked a certain color. Never, not once, they didn't pick that color. Turned out that on the inside of the brown paper bag, one of the little folds on it was pulled up. Dude got stuck underneath there and stayed under there the whole time. Was that a variable that influenced the experiment? It was. We had no idea until at the very end when we analyzed it and said, hey, something else is going on. Did you do your math right? Yes. Did you random draw? Yes. Shook it up, didn't look in? Yes. There's got to be something, and that's when we looked a little bit further and says, oh, there it is. It's got stuck in there. So going back to having this one where we expect it to be rejected and it wasn't. Well, that's the thing. What we're using for a probability value is what? What is our probability value, our p-value? That means that we are 95% sure that when we run this analysis that the data is going to reject it, or we're 95% sure that when we run that, the data fails to reject it. 95%, because every once in a while there's a little nugget that falls outside that range because something could be due to chance. There was one year that I had a student purposely, after a few draws and saw what was going on, and admitted to it, that they purposely shunned the big one aside and got one of the little ones. Because they were like, oh, what are you going to do now? Oh, that's perfect because it proves 95%. It's perfect because it proves 95%. Most of the time in the class period, everybody gets it rejected. So it's nice to see every once in a while that that's shown. And that tells us that every once in a while there's something outside of our control that's going on that's messing with it. There's a variable that's acting on it. Or it might just be up to chance. Hang on. Okay, she'll be there in like about 5 minutes. Okay, thanks. Bye. Finish this up real quick and then so where was I at? Okay, so like I said, that's perfect. That proves our 0.05% probability that there's always things that are outside the line. Okay, post-it note. We've been talking about dysfunctions of the heart. Oh, and in fact, you won't listen to my melodious voice, so I'm going to turn that upside down. Does anybody remember what atherosclerosis is? Build up a plaque in the arteries, and what does it do to our blood pressure? Raises our blood pressure. What's the middle of that blood vessel called where the plaque is building up? So the lumen gets closed off because the plaque builds up. Is that a short-term thing, long-term thing? It can be a pretty long-term thing, depends on if you get treated. Are you born with atherosclerosis? Probably not born with it. It usually has something to do with diet and something to do with genetics. Palpitations, do you remember what those are? Heart flutters, long-term? No, so skip a beat, heart flutter, something like that, but it's a very short-term thing. Mitral valve prolapse, or valve prolapse. Doesn't close properly because it does what? Describe your sign language there. So you did something a little bit like this. It's bulging up into that atrium. So bulging up into the atrium, if it bulges too much, what might happen? Regurgitation, which means blood's going the wrong way because of the fact that we have a gap there. You can be born with that. So some of these diseases have different terminologies that are associated with them. So congenital. Mitral valve prolapse could be a congenital issue. If you have a septal defect, that could be congenital. Congenital is a dysfunction or disease that you are born with. Nathaniel, we want to write this down because these terms are going to come around. Congenital is a dysfunction or a disease that you're born with. Congenital heart disease, it's entirely possible to be born and have heart issues. Chronic. Atherosclerosis might be chronic. High cholesterol could be chronic. You have that your entire life, so it's long-lasting, continuing. Acute for our diagnosis terms. That means it's immediate or it comes on suddenly. And so these would be a good place to put that with our heart dysfunction information. So you can put it right smack dab with your problematic heart stuff. Congenital, you're born with it. Chronic, it's long-lasting. Acute, hopefully acute isn't long-lasting too, but I guess it could be acute and chronic. But acute comes on suddenly. Smack that somewhere with your problematic hearts, then turn to an empty page in your PBS course file, preferably one or two of them next to each other, because we're going to put an insert in, but not today. So we've talked about organ systems, and I've mentioned the fact that organ systems work in conjunction with each other. So, they don't stand alone. So feedback loops are an important concept. There are two major types of feedback loops. The first one is a positive feedback loop. A positive feedback loop is when we have a stimulus which amplifies a result, which creates an increase in the stimulus. So more stimulus means we amplify the result, which creates more stimulus, which amplifies the result, which creates more stimulus, which amplifies the result, which creates more stimulus. So positive feedback loop, a stimulus amplifies a result, which creates an increase in the stimulus, which amplifies the result, which creates an increase in the stimulus. Which amplifies the results, creates an increase in the stimulus. One of the better examples of a positive feedback loop is kind of like global warming. So you wear a white t-shirt in the middle of summer. Why do you wear a white t-shirt and not a black t-shirt? It reflects the light and the heat. The black, dark stuff is going to absorb more heat and make you hot, whereas white will help keep you cool. Same thing for the poles. At the poles, we got it covered with lots of snow and ice and white stuff. So it's reflecting a lot of the sun's energy and heat. Let's say it warms up just a little bit and some of that snow and ice melts and the ground is exposed. What color is the ground? What color is the ground? Brown, green, darker colors, yeah. So sunlight hits it. Does it get reflected? Nope, because it's darker, so it absorbs the sunlight, heats the ground. The ground heats, what happens to the snow around it? Melts, exposes more dark green, brown ground. More sunlight gets absorbed, heats the ground, what happens to the snow? Melts, exposes more. See how that's a positive feedback loop? In our body, positive feedback loops are helpful because they can get things done quickly. A good example of a positive feedback loop is childbirth. So when those hormones are released, it creates a stimulus, which releases more hormones, which creates a stimulus. So we want to get that done fast. You don't want that to take weeks and weeks and weeks. Blood clotting is also a good example of a positive feedback loop. When you cut certain cells, there are hormones that are released that attract platelets, which attracts more platelets, which attracts more platelets. And so we want that to clot because we want the bleeding to stop. However, most of the feedback loops in our organ systems in our bodies are negative feedback loops. And negative feedback loops is when a stimulus leads to an opposite outcome. Negative feedback loop, a stimulus leads to an opposite outcome. And it has a general figure 8 shape, but it's not always exactly a figure 8 shape. So I have a stimulus that leads to a decrease in a certain substance. Another stimulus leads to an increase. So an increase in something leads to a decrease in something else. A decrease in something leads to an increase in something else. And so that helps us to maintain homeostasis, which is what we want to do. We want to keep everything balanced and just right. Okay? Macromolecule notes are due on Monday. There are inserts for that. Tests for PBS is Tuesday. CBC notes are due on Wednesday. There's inserts for that. Make sure you're taking care of business. Have a good weekend, and I will see you on Monday.